Alright, so now we're going to take a look at the bisection method. For our first algorithm. And so in this algorithm we're not actually looking for a minimum. What we're doing is we're solving for where g of x is equal to 0. And the idea comes from the intermediate value theorem, because the IVT says that if g is continuous on the closed interval from a to b, and g of a, well, I'm changing it a bit for this application because I'm looking for where g of x is equal to 0. In general, this would be like g of x equals n. Yeah, and so if g is continuous on the closed interval, g of a and g of b are opposite in sign, then there exists a c such that, are you guys familiar with that backward z? That there exists c such that c is in AB. Okay. Such that g of c equals 0. And so it's easy to see that, right? If you have g of a is negative and g of b is positive, then the only way you can get from one end to the other is by going through the middle. Okay, but of course that's only if g is continuous, right? Alright, so in this case this would be the middle. Okay, so we're going to start with this, and what we're going to do is we're going to say, well, I know if g of a times g of b is negative, then I know that g of a and g of b are opposite in sign. And so I'm going to take half of the interval then. So c is going to be my midpoint. And now I'm going to check f of c, or g of c. Excuse me. In this case, g of c is positive and g of a is negative. So therefore I know that the new interval is contained, or the 0 is contained in the interval from a to c. Right? If g of c had been negative, right, then the new interval would have been from c to b. And then you go into this interval, and then you cut it in half, right? And then in this case, the new interval would be here, and then you cut it in half, and then the new interval would be here, and then you just keep going over and over and over again. Alright, so let's see if we can write that down. Alright, the bisection method is very simple. We initialize with, I guess I'm using f of x in the notes, so I guess I'll use f of x here. We need the f of x, we need the interval from a to b, and then we need to know that f of a times f of b is less than 0, so that should be part of the input. Okay, so then in the algorithm, maybe I'll just say step 1. Step 1, we'll go ahead and evaluate. I'll call this f sub a is f of a, and f sub b I'm going to go ahead and set to be f of b. This is like my computer, right? I'm evaluating my function at these 2 points. Good. And then here's the main loop. Set c equal to a plus b divided by 2. And then compute f of c. Good. And now we check. Let's see, which way should we check first? I'll stay with notes. If fa times fc is less than 0, what did we say? The new interval was in the interval from a to c. Right? And so we reset the interval, so a equals a, you don't really have to do that, but then b, the new b, is equal to the old c, right? And then you also go ahead and reset your f of b, because you've already done that function evaluation. Okay, else, well, if it's not there, it's got to be in the other one, right? So therefore, um, well, I should say there is a slight possibility that f of c is equal to 0, and so you might want to check, because then you would be finished, right? Otherwise, the new interval is the interval from c to b, right? And so then you reset a to be equal to c, and then b is equal to b, and then also reset f sub a to be f sub c. Good, and that's it. Repeat. Of course, that would go on forever. So the thing we should be thinking about then at the end is, what should the stopping criterion be? And I've listed a couple of them. One choice would be to say that the difference between, or I guess one way to do it would be to say that the size of the interval divided by 2, which is going to be at the end, right? Because when we're finished here, we should return, I didn't put this in here. At the end, you want to return A or B. The choice is neither. Return C. So this is the value that you would send back output from the function. Okay. It looks better on the notes. Okay. So one stopping criterion would be that the interval size is less than some tolerance, right? So that way you know the solution is somewhere in the interval, and so this is checking the tolerance on x. You could also check the tolerance on y, and so you could say, well, is the absolute value, geez, I'm writing it like computer code, is the size of f sub c less than some tolerance, right? Because we're checking, we want f of x to be equal to 0. Good. And then the last thing you would want to check is, has the max number of iterations been attained? Right, so this is just a safety so you don't get an infinite loop. Although at some point, I guess you've got to get the tolerance, right? So I guess you don't really need that last one. It's always good to have some safety procedures there, just in case things don't work out. All right, so this method then is very, very simple. I'm going to let you try one by hand. That's the first homework problem in this section. Okay, we're going to take a look at the next one. By the way, what information about f of x did I need in order for this to work? Number one, maybe I should write this down. What info was needed here? Just f of x. And a solution that was bracketed. So, and you needed to know that you had an interval where you had a solution. Good. All right, so by the way, to use this for optimization, we don't look for the zeros of f, right? We look for the zeros of the derivative, right? And so that's how you use a root finding algorithm to find the minimum and maximum. You're actually looking for the critical points. Good. All right. And so the next one's probably the most popular method around, but of course it also it's very fast to converge, and well, we can take a look at it first. So next up, Newton's method. Actually, some people are calling it, well, some people, Newton-Raph's method. I always leave off Raphson and just leave it Newton. That's the way I grew up with it. It's Newton's method. But Newton has a lot of things named after him, so. Alright, anyway, we're at 10 minutes, so I'm going to stop here, and in the next video we will derive Newton's method.